So in today's lecture, I'm going to actually cover two things. Oh, thank you. Appreciate it. I'm going to cover two things. First thing is I just wanted to finish up some leftover items from our discussion last time on estimation. And to communicate again, to emphasize again a couple of key take-home messages that I want you to get out of the estimation lecture. It's a lot of stuff in that lecture, and things that are absolutely key messages get mixed up with a lot of detail on methods I want you to know about, that they exist and that you can use them, but I don't expect you to remember everything about them, okay? So there's a lot of stuff with statistics and so on. I don't expect you to systematically know all of that so you could do an example like that, but I do expect you to know that it exists and generally what it accomplishes. We'll be finishing up some components of that in a minute. These are the key take-home messages that I'd like you to carry away from that lecture. First thing is we're dangerously poor at estimating for two reasons. Number one, generally we're sort of systematically inaccurate. So we're over-optimistic and we're too confident about our answer. We think it will take a lot less time than it does often. Moreover, we think that our guess is a lot more accurate than it really is. We think we're a lot more confident about our ability to estimate it than we should be. You imagine a situation where you tend to be over-optimistic, but you say there's a really wide range of variation, maybe off by a factor of 2 or 3, but we tend to cling to this notion that we're actually pretty good at estimating things. So that's one issue. We're systematically inaccurate. Secondly, we're inaccurate in a way that is systematically dangerous. Dangerous because it errs on the dangerous side. It errs on the side of being optimistic, okay? On the side of making the situation more difficult if we're wrong. And all these things combine for the fact that a lot of projects fail or are judged to be failures because of poor estimates. Now, some of the reasons for that is not just that we're bad at estimating, but we accept as software developers, as software engineers, we make the mistake of confusing a couple of things. We, for example, have a guess and we use that as an estimate. It's not a well-founded, well-thought-through, informed guess. It's just what they call a wag. Anyone know what a wag is? Wild ass guess. So, well, I think it'll take roughly this amount of time. And then we get called to account for it later. Or we mistake a target, something we're hoping for. Maybe it's something we'll shoot for as a team, with an estimate. An estimate should be something that's fundamentally realistic based on evidence. And it's not just one number. We'll get to that in a bit. An estimate should be made by the technical team. All too often they're made by managers and handed on to the technical team as something they have to meet. And that's not an estimate either. That's a constraint, and a somewhat artificial constraint, and it may have little or no bearing with the actual amount of time it's likely to take. It's what the manager hopes it will take, maybe to advance their career, because it'll be convenient for them. And software engineers often are not at their very finest in the human feature of things, in dealing with these issues. And sometimes they just kind of accept this so-called estimate given to them, this so-called target, the final date, as if it's an estimate. And it's not. They think it's easier to just accept it and work with that than to say no. And it comes back and bites them later. But as they say in China, the mountains are tall and the emperor is far away at the time. That will be down the road 6 months from now or what have you that will be called to account. And it's easy to imagine that it might not happen. It might not actually come about in a bad way, and it's easy to kind of say, yeah, I guess we could do it. We can really work hard. We're a good team. And that way lets disaster off. You accept something that's a couple months shorter than the amount you think it will take, and you end up in a bad way a number of months down the line with your great morale, previously great morale shot, your team having lost a bunch of people, barely scraping by, your client unhappy. And all something you could have avoided by setting expectations right and just resisting the pressure to accept one of these wishful ideas of when it should finish that was thrust upon you by a manager. Gotta learn to say no. So you gotta resist pressure to set estimates optimistic. This is not a minor thing. It happens a lot. It happens a lot from pressure from above, politically. Another key thing, this is one of the most important, folks. You forget everything from that lecture. Remember, please systematically try to use in your work range estimates. They force you to think through sort of a plausible best case and a plausible worst case. And even if you're somewhat off in these, at least you've thought through, or you've been pushed to think through, what things could take longer than we expected. What things could we be off on? And that's important. That's important because it may wake up to the fact that there's actually some danger of long range. It also signals to your managers, to those above you, and there will often be people above you, it'll signal that there's uncertainty here. You're not committing to one date. You're not committing to one period of time. You're not sure about these things. And that may start a dialogue. They may ask you, oh, so why is it so broad? You say, well, there are these things we're worried about. This risk, that risk, etc. And that may clue the manager into certain things they never knew were big uncertainties. And it may be that some of those, if they give you the right resources, could be resolved. If they said, oh, don't worry about that feature then. That feature? I mean, you're worried about that? That was just one stakeholder's desire. Forget about it. Exclude it. Maybe that would narrow your range of uncertainty a lot, because you don't have to worry about certain weird technical cases. So use range estimates. They'll start dialogues, and they'll give you the opportunity to avoid reflexively just giving an optimistic number by forcing you to think things through. And they can set expectations in a far more grounded way than just giving a number. And communicate sort of the difficulties that might be there. Okay, and then finally, and this is what we'll jump into right now with a few concluding remarks. To estimate a task, we reason about its pieces. We do estimation by decomposition. If we have some sizable task, maybe it's your next milestone, and it has these pieces which have to be done for it. In order to estimate that, you don't try to estimate it as a whole. You break it apart into its pieces, identify those pieces, think them through, and give range estimates, perhaps best, most likely, and worst cases for each of them. And that will allow you to work towards estimating the whole. But you can't simply total those up to get the similar values for the whole. You can't simply total up the best cases for all the pieces and expect to get a realistic best case for the whole. You can't total up the worst case for all the pieces and expect to get a realistic worst case for the whole. It doesn't work that way because of the probabilities involved. So I just want to finish up that topic because there's a lot of pieces there, and I want to remind you of the essential things. So we went over, a lot of stuff last time on sort of causes for concern, etc., and we came down to this issue of decomposition. The idea is that for each of a set of pieces of a broader task, say here features, we identify best, a most likely case, and a worst case. And we figure out by applying a formula, a mean for that, okay? And the formula is in a slide here. To derive the expected value, the average value, you can more conservatively estimate it as this, or less conservatively estimate like that. So, ladies and gentlemen, point one, in terms of this thing, you are estimating these features, these pieces, and you want to get an estimate for the whole task, right? People comfortable with that idea? Okay, so you estimate for each of them, best case, worst case, most likely case. You use that formula I just showed, one of those two formulas, I'd suggest the conservative one, to get an expected case. Great, get an expected value out. And you can total those up to get the expected value for the whole. However, to get the range around this, the degree of uncertainty about it, that's going to require a bit more finesse. Does anyone remember some element of that we talked about last time? How are we going to get a range of uncertainty around this guy, like a standard deviation? Yes, exactly. We could compute the variance of these guys to try to estimate the variance of the whole, okay? And fundamentally, the variance is, in the case of independence, and that's a sizable assumption here, in the case of independence, we can add variances to get the variance of the whole. The main problem, though, often the biggest problem is not the non-statistically independent, although there's some concern about that. The biggest problem is that often these best and worst case estimates we give for the pieces are very, very inaccurate in the sense that they are way too narrow. We have too much hubris about it. We have too much confidence about the accuracy of our estimate, and therefore we make those ranges too narrow. We saw it on the board last time, right? We didn't put a broad enough range in to capture the 90% confidence intervals around the true value. So in the event that our best and worst cases were indeed 3 standard deviations out, we could just take one minus the other, divide them by 6, and we could end up with a estimate of standard deviation for each of these. However, we can't do that. And so generally what we do, and this is the piece I wasn't able to cover last time, generally what we do is we try to use historical values to sort of figure out how overly tight are our estimates, okay? If historically our best and worst case estimates are such that the true value only falls between them 30% of the time, it suggests they're too narrow, and we can try to correct for that. We'll try to correct for the fact that we give overly narrow estimates, okay? So we try to look, okay, let's look at the times where we estimated this thing. What fraction of the time did the real value fall within that? If it only fell within that 10% of the time, we're going to use a correction factor here that will end up correcting for this fact. If on the other hand, our estimates are indeed 3 standard deviations out like that, we can divide by 6 here. More often, maybe our estimates, the true value will be 50% of the time within our estimates, the best and worst case. In which case, we'll divide by 1.4. So we're going to get a value for the standard deviation, ladies and gentlemen, of each of these guys here, each one in turn, each of the pieces. We're going to get it by this formula here. We take the worst case minus the best case divided by the correction factor as determined by our historical performance in estimating. So if we're only right 50% of the time, if it's a coin flip as to whether or not it lies, in fact, in our range, we're going to be divided by 1.4. Does that make sense? To get a standard deviation for each of these pieces. just like that. And we've already estimated the mean here. We're going to be estimating the standard deviation. And from that, we're going to be able to work towards an uncertainty for the whole. So here's best worst case. We derive the standard deviation. We square it to get the variance. We can sum that up, take the square root. The variance, remember, is the standard deviation squared. We write variance as sigma squared, right? Folks have seen that before? Yeah, okay. And standard deviation is just sigma. That's the thing which we are just calculating here, right? For each piece. So we total up. We compute the standard deviation for each piece. We compute the variance for each piece. We sum that up. And we take the square root to get the standard deviation for the whole. What does that give us? That gives us now two things. One thing is the standard deviation for the entire task, and one thing is the expected value for the entire task. That is what we were seeking. Okay? That's exactly what we were seeking. And then you can calculate confidence intervals around that expected value using this value of sigma for the entire task. And this is just a standard normal distribution. So if you want, if we want to find certain confidence intervals around that, we can use the expected case in the standard deviation. There's some assumptions there, but the essentials are in that method. Okay, so those were just the comments I wanted to give about this method. The main points, and I wanted you to know this method is available. It's available as a point of reference. I'm not going to be testing you on the details of this method. Okay? I am, however, I do expect you to be responsible for knowing something about the essentials here, and probably knowing something about what things we ask the person who's doing the estimation to give, things like best case, worst case, most likely case, and what things are derived. Things like the expected value, in other words, the average. Things like the standard deviation. And to know something about the fact that we will correct when the standard, for the fact that our estimate of the standard deviation, if we did it naively, it would be off. We correct using historical data. Any questions about that? These are the important points I want you to take home. Okay? Okay, so that's going to close my comments on estimation here. I do want you folks in the course of this lecture